This is lesson 5.2 on perpendicular and angle bisectors. So first of all, a perpendicular bisector of a triangle. We have talked about what a perpendicular bisector of a segment looks like, and that's what you're seeing here in this picture. A perpendicular bisector, remember, it hits a segment at its midpoint, and it also makes a right angle. So for a triangle, a perpendicular bisector is the same idea. It's just that we're talking about in relation to one side of the triangle. So considering this one side to be a segment, a perpendicular bisector will be perpendicular, making a right angle, and it'll hit at the midpoint of the segment. So you have to have both marks, the perpendicular mark and the congruent segments on the side. So obviously, since a triangle has three sides, there would be three perpendicular bisectors. So there would also be one here, and there would be one here that would be hitting the midpoint of each of the sides and bisecting it. And then an angle bisector of an angle we've talked about. An angle bisector is what is shown in the picture here. So this is an angle bisector because it's cutting the angle into two congruent parts. And so for a triangle, if you pick one of the angles, an angle bisector is a ray or a line or a segment that divides an angle into two congruent adjacent angles. So obviously, again, also you could bisect this angle and you could also bisect this angle. So any triangle would have three angle bisectors as well. Now notice that a perpendicular bisector does not have to go through a vertex of the triangle. The vertex over here is not lying on this perpendicular bisector, whereas an angle bisector has to go through a vertex, just the nature of the fact that it's an angle bisector is going to cut the angle in half, so it must go through a vertex of the triangle. There are going to be 4 theorems that we talk about in this lesson. So the first 2 have to do with perpendicular bisectors. So the idea is if I were to stand at the front of the classroom, so let's say student A is sitting here and student B is sitting here. If I want to stand in the classroom at a point that is equidistant, that means the same distance from both of those students, where should I stand? Well, if I stand here, does that work? No, because I'm closer to student A. What if I stand here? Nope, I'm closer to student B. So the idea is, in order to be the same distance from both of the students, I need to be somewhere like here that I can tell those distances are the same. Or here, where I can tell those distances are the same. Or maybe even at the midpoint of the segment that would be joining them, then I can tell those distances would be the same. So it turns out that where I would be standing would be somewhere on the perpendicular bisector of the segment that would be joining students A and B. So if we draw this segment and then we draw the perpendicular bisector, anywhere that I stand on that perpendicular bisector would place me the same distance from student A as I am from student B. So that's what's going on in the perpendicular bisector theorem. So there's a theorem and the converse of the theorem. So first of all, the theorem says that if there's a perpendicular bisector of a segment and you place any point on that perpendicular bisector, so if you pick any point that you know lies on the perpendicular bisector of a segment, and you can tell that it's on the perpendicular bisector because of the perpendicular mark and the 2 congruent segment marks there. So if we pick a point on the perpendicular bisector, then the distance of that point from both of the endpoints of the segment is going to be the same. So if a point lies on the perpendicular bisector of a segment, see how we're starting with the perpendicular bisector? That's why it's called the perpendicular bisector theorem. If a point lies on the perpendicular bisector of a segment, then it is equidistant, the same distance from is what that means. The same distance from. Oops. Okay, it is equidistant from the endpoints of the segment. So the distance from that point to each of the endpoints of the segment, these distances will be the same. Now the converse is going to say something very similar, but again, a converse means you're reading it backwards. So we're starting the other way. Now we're starting with a point that we know lies the same distance from each of the endpoints of a given segment. So given segment xy, if I pick a point that's the same distance from x and y, then where is that point going to lie? That point must lie on the perpendicular bisector. So here we're starting with the distance of the point from the two endpoints being the same, and we're ending with stating that that point must lie on this perpendicular bisector. So again, it's applying the perpendicular bisector theorem if you start with knowing you have a perpendicular bisector. It's the converse if you're ending with it being a perpendicular bisector. So perpendicular bisector theorem is kind of like the isosceles triangle theorem. You know this is a perpendicular bisector, then it's perpendicular bisector theorem. Take a second to look at the next two problems. Pause the video and decide whether you think it's the perpendicular bisector theorem or the converse that's being applied in each of those situations. Okay, so in the first problem, they're asking you to determine the length of segment XW. Well, you can tell in the picture that this is a perpendicular bisector. Therefore, you're using the perpendicular bisector theorem. So because x lies on the perpendicular bisector of segment YW, it is the same distance to each of the two endpoints. So x is equidistant from y and from w. And then in the second example, you can tell that E is equidistant from the endpoints of the segment AF. So because these are both 19, that means that this point must lie on the perpendicular bisector of this segment. So that must be a right angle and these must be congruent. Therefore, BF is equal to 4.2. This is the converse of the perpendicular bisector theorem because you're not given that it's a perpendicular bisector, you're using the equidistant in order to get that it's a perpendicular bisector. So if you know it's a perpendicular bisector in the problem, then it's the theorem. This one would be the converse. Okay, for the next two theorems, you're going to need to know another definition that we haven't talked about yet. So in this diagram here, it's showing you a line L, and there's a point B and there's a point A. Now, in order to talk about the distance that point A is away from line L, imagine that you're standing here and somewhere in the classroom, and this is the front wall of the room. If I asked you how far away you're standing from this wall, you wouldn't tell me, oh, it's like however far that is, or it's however far that is. If I said, how far away are you, you would figure out the distance that would be the shortest distance, which is, again, the perpendicular distance from that point to the line. So the way that the distance from a point to a line is defined, it's the length of the perpendicular segment between the point and the line, which corresponds to the shortest distance. So again, if I asked you how far away point A is from L, you would measure the perpendicular distance here. Or if I want to know how far B is away from L, it would be that perpendicular distance. So these little segments are representing the distance of point A from line L and the distance of point B from line L. Again, this is something you have to understand in order to be able to understand what's going to happen in the next two theorems. All right, so we have two more theorems here that are analogous to the perpendicular bisector theorem. That means they're really the same idea. It's just dealing with angles instead of segments. So, same idea. If I told you that you picked a point that's the same distance from both sides of an angle, which is like down here, then that would mean that that point is on the angle bisector. Or if I wanted you to stand somewhere on the angle bisector of the angle, then that would mean the distance that you are away from the two sides of the angle would be the same. Okay, so the angle bisector theorem says if a point lies on the angle bisector of an angle, it is the same distance from the sides of the, and that should say angle on yours, I think it's corrected. So remember that you measure the distance from a point to a line as the perpendicular distance. That's what I was talking about just in the very last slide. Okay, so this says if you know you have an angle bisector, which you would be shown in the picture that those angles are congruent, if you pick a point on the angle bisector, then that distance, the perpendicular distance from that point to each side is the same. So notice it's going to be drawn perpendicular, and those distances are marked congruent. So the distance from P to T and P to F would be the same. Here we're starting with an angle bisector and saying that that would make that point equidistant from the sides of the angle. The converse would go the other way around. So in the converse, you're given a point that is the same distance from two sides of an angle. If a point's the same distance away, I couldn't pick it like here, for example, because that's closer to it's closer to this side of the angle than it is to that side of the angle, right? So in order to pick a point that's the same distance from the two sides of the angle, it's going to be kind of like the halfway in between the angle, which means that it will be lying on the angle bisector. Now notice that when it's drawn, it's not just an angle like this where you're saying, okay, I'm going to pick a point here and these distances are the same. The distance that as you measure it, has to be perpendicular. So when you start with an angle, if you pick a point that's the same distance, it has to be the perpendicular distance, like that, is marked the same. And then that means that it must lie on the angle bisector. So if you were to draw the angle bisector, that's a terrible picture. Let me try that again. If you were to draw the angle bisector, then that point would have to be on the angle bisector. So if this point's the same distance from the two sides of the angle, then that point lies on the angle bisector. Okay, and that's what you're seeing in this picture here. So given a point equidistant from the sides of the angle, it must lie on the angle bisector. Now again, pause the video for a second, look at that those next two examples, and see if you can figure out which one is the angle bisector theorem and which one is the converse. So in the first example, you're shown that the distance, perpendicular distance, from E to A and E to C is the same, which means that E is the same distance from the two sides of the angle. Therefore, E must lie on the angle bisector, which means that ray BE is the angle bisector of angle ABC. So if this angle is 43 degrees, then this angle would also have to be 43 degrees. Now, that is the converse because you weren't given it's an angle bisector. See right here, it doesn't show you it's an angle bisector, it's showing you the distance over here. So this one's the converse. The second one is the actual angle bisector theorem because it's saying, oh look, this is an angle bisector. Angle V is being bisected by ray MK. And therefore the distance, which, see how they have the right angle marks there? Those right angle marks are necessary in order to show that the distance that's being measured is the perpendicular distance. So you're for certain that those are both representing the actual distance from K to each side of the angle. So the two parts would be equal. Km and KT would be the same. So you can make them equal, solve for x, you get x equals 9. Now it asked you for the length of MK. So plug it back in and you would get 19. 2x plus 1. 2 times 9 plus 1 is 19. This is the end of lesson 5.2.